Let's continue. So I left you with this example, and yeah, let's see who's able to solve it. And there's a few discussions, and a bit more discussion really, which we can have. Okay, so a mass falls from a height of h meters onto a collar on to a fixed end of a steel bar in diameter and 1 meter long, right? Okay, so this is a typical problem for impact energy. Yeah, and what they require is the maximum height, as long as you don't exceed that stress, the maximum instantaneous and final elongation, so that's going to be interesting to see, and the maximum and final strain energy stored in the bar. Assume a modulus of rigidity of 200 gigapascals. Okay, so what is the first approach you take? What did you do? Can anyone mention the first approach?
MGH or MG, sorry, find out your potential, your P.
Yep. Yes, MGH, but remember,
No.
Yeah.
Because without the H, your mass times your gravity, so basically your force, you can work out your P.
Yeah. So we're looking for H here, by the way.
Yeah, but you will use that when you're finding H.
Are you just calling it P? Or is that what you're saying?
Yeah, I'm
Okay,
using the same.
Fine. No, you call it, it's fine, you call it that. This is 8 point, what's this, 8.5 again, right? 8 point, let's get this number right. Yes, MGH, right?
Well, I was basically using it as the weight. You're finding the weight of that 30 kilograms, so which is 294.3 newtons.
Yeah. No, but I mean, like,
Okay.
what do you know? Fully equated to, man. I mean, I
Yeah. And
MGH
then,
plus what? I mean, this, so it's H plus deflection, right? Remember this? I'm talking about this.
okay, yeah.
Energy, yeah. That's how I'm
Yes, that's it.
Okay.
Yes.
Yeah. So you are in essence right. Okay, so they want that instantaneous stress induced by the load falling on the collar. So as Alex said, that 30 times 9.81, this is that 209 something you mentioned. H we do not know. And of course, this guy we can change into stress LE, if I'm correct. You're able to do that. And so that stress, the length is 1 meter, and then we just divide it by what is this again? What's my 200? Yeah, because we're looking for this guy. Oh, we have this guy, sorry, which is 80. My bad. Yeah. Excuse me. Yep. And then again, that's the max. So what it basically means, we look at your curve. I guess it's not to exceed the yield value there, allowable stress. 2 times your modulus in times of volume. So it's pi over 4. It's a really easy chapter times 1. All we have to do now is just basically, I'll have it like this. I'll just work it out for you guys quickly. Sometimes I ask you to find the stress. That's why I was looking at that now. That's a very standard example where they ask you to find the stress instead. So yeah, just making you aware. Pi over 4 times 0.02 squared times 1, and then just divide by 30 times 9.81. I think that should be okay. I got 213.4959 times 10 to the negative 12. And what I'll just do now is, should I just carry this over now? This doesn't feel right because now I'm going to end up with a negative value.
No, so it does feel right. It's.
What am I looking at here? Yeah, I'm listening.
Yeah, that's the procedure. It's gonna.
Yeah, I know for sure. I'm sure I'm correct, but what is my,
You have to,
I think
I
I'm,
think the 30 times 9,81 should go the other side, divide.
yeah, no, for sure. I did that, man. But I think I made a mistake somewhere with the numbers. I'm sure the procedure that I mean, I just think yes, I have that value, then divide by 30 times 9,81. Yeah, no, it's right. But what I'm saying is if I carry this over, I'm not
Yeah,
going to
the
get my
80
answer.
is to the power 2. I don't know if you put to the power 2. The stress.
Oh, I see. Yeah, that's my mistake. Yeah, there we go. There we go. Squared, yeah, that's squared. There we go. Thank you. Sort it out now. So I'm not sure what this is over here now. But let me just recalculate. It's always squared when you're working with the strain energy. Yes, there we go. Looks a lot better. 30 times 9.8. So I get this. I'm hoping this is right. 0.96 times 10 to the negative 3. And of course, I'm just carrying that over. And of course, this one is not squared now. And if you get that, you carry this over, your height should be 16.67967 millimeters. All right. Okay, so that's the answer there. Looks good. They say now what would be the maximum instantaneous and what would be the final elongation? Zakasa, you asked me this question, so you're gonna go here, change your length instantaneous and change your length. So who can tell me? And this is change your length max. Who can tell me for instantaneous, we're just gonna use stress given L over E. That is correct. Yeah, I can hear someone reading. Of course, it's times 1. So that's my instantaneous. So how will I get my max value? Who can tell me?
We're gonna
Should be
have
full time.
the load
Yes. Why the load though? So
for
it's
the
30 times
for the
9.8.
final.
Yeah. I'm using flea or flea.
Flea, yeah. Okay.
Yeah, flea. Yeah. So why is this the maximum one? This is what I'm trying to check. What's that area again? 0.03.
It's the final or the maximum.
It's the maximum. Final elongation. Yes, that's what I meant, man. It's the final elongation. And if you do that, you should get that answer of what's it? What's the answer here?
I got 4,684 times 10 to the power minus 6, which is 0,005.
So do we agree with these answers though? Are we happy about it? Do we understand what it means? Times 10 to the negative 6, right?
Negative 6.
Yeah. Okay, so let's just get a small conversation happening here. Is it Yebo now? Oh, that was Alex. You've answered this question. Did you get the final elongation?
Yeah, I got it.
Okay, but you understand the difference between the two answers? Like what?
I'm trying
to
understand the difference. I don't
Yeah,
know
so
yeah.
this, if you compare that, like the magnitudes, right? So they have 0.4 and they have what? 0.0047. We get that, right? I'm just using the two values they given, which is the same as this. On impact, right? It's a pity I don't have like a like a spring kind of setup here, and I think what I'm trying to show you is that like on impact, I don't know how to actually just put the color here. Like when the mass falls, right? It extends 0.4. Like it has its maximum at the when we drop the load. it goes down 0.4. However, when it settles eventually, right, and it settles to, obviously to this load over here, this 30 times 9,8, we get 0.047. The final, just a weight rest. Yes, exactly. It's just a weight resting on the collar. So it falls down, and then it gets deformed by 0.4, and then eventually, obviously, it reverts back to the original position, and all that's left is in essence the weight of the column, and that's all it really means. So obviously, with a strain energy, what can we use for strain energy? Just so we have, what model do we use for strain energy here? So what model do you use? You can use
the log P.
Yep.
Bracket
H plus
delta L, instantaneous.
Yeah. So let's see for this one. What is my load, by the way? Because I mean that's not very clear there.
294,3.
294. Are you sure about this? Let me check. 294.3. My height was 0. We found height now. 16 something. 16.68. Plus the change in length there. Okay. Yep. Beautiful. It's 2943 plus that 16.68 times 10 to the negative 3 plus that 0.4. Can we do the same thing? Can we do the same thing on the other side as well? So this is going to be obviously on impact. It'll be more. It's a more energy extense of 5,027 joules. Yeah. Can we do the same thing over here? You think we get the same answer? We just have to change the extension there to 0.0047. Do we get the same answer? Let me just quickly see. What's the answer for the next one? Nope, doesn't seem to check them. Oh, there's negative 6. 0.04 point. But you see, the maximum one is not so. The maximum one shouldn't be that simple. Yep, it's a 6. It's the maximum one. Yeah. So how do we find now our? How do we find our? What do they phrase it as? Our final strain energy. Remember, that's just the instantaneous one, right? So that makes sense. That's on impact. But this impact. So how do we find that one? Remember, it can also be considered as a gradually applied load, and there's really different ways to. It's negative 6. So in this case, it's half PL you can have, and half times 294.3. So that's why one must be, because this is like a gradual pilot, that's now on impact, and that's going to be times that length. Really plug and play, guys. I think it's just a matter of very basic interpretation. So this, I get 6,891 times 10 to the negative 4 joule. I hope this is correct. Yeah, it looks okay. Okay, is there any questions with this? Get a few thumbs up. Otherwise, any questions? Any questions, students? Before we move on. People still here. Motaso, also, sorry. Sindima. Grandson, no questions? Okay, yeah, it's very simple, guys, really. Yes, Mr. Abreu.
Yes, sir. Please, can you explain again the relationship from the beginning, the relationship for MGH and the stress? Because I don't get it from there.
Okay, from here.
Yes, from the beginning.
Okay, very good, very good, very good. Okay, so do you remember that? Do you remember there's a question similar to this for the springs? You know, where So okay, let me just start to sketch this correctly. I'm just thinking of a proper sketch here. Just give me a second. So you know, a collar looks like it's like a bar here. And then basically there's something at the end here, right? So imagine there's some kind of mass, kind of like, you know, I'm doing it very around this, and this is the collar here. So the reason why we have this relationship, right? The mass will fall through height h, but as it falls here, what happens is it will induce a change in length within the body. So that is why we say h plus change in length. And of course, if this is in joules, obviously that's potential energy. The potential energy is essentially converted into your strain energy in this case. Does it make sense? I don't know if
Yes,
I
I get it now.
Okay, thank you. Cool, guys. Really, it's not really much to talk about there. But let's move on. It's going to be quick. And it's not really much to do after this. And you guys can really just go in and just get yourself acquainted with this. And yeah. So we have two different, this is the question obviously, but we have two different setups. And so this is just back to your normal static and compatibility equation. We have two members there is a nice color there, which they explain quite nicely. So your forces are equal in both members, and what happens is your change in length, or they're calling it D here, as per the slide. It's just basically the sum of the two lengths is back to like strength 2. The only thing what's important, you have a new relationship, and that is U1 plus U2, the strain energy stored in the first part. The second bar is equal to the total strain energy. So yeah, that's basically that. And also, this is for parallel, a similar setup. So you can see a parallel arrangement. So there's one material on the outside, which is a tube or some kind of pipe, and inside the pipe we have basically a steel rod, the typical arrangement. And of course, what you see there is some collar P or some weight P and a collar at the bottom. I'm sure actually just see with these images. Of course, your forces here are equal. Your forces are carried by both members, and your change in length is equal. So obviously, as per normal, and your strain energy would be the sum of the two, basically. So it's obviously your strain energy in the one plus strain energy in the other one will give you the total strain energy. So I don't think there's nothing more to explain. What these relationships are fairly self-explanatory here. However, one must always be cognizant of whether loads are being gradually applied, suddenly applied, or it's impact load. So we must always just be aware of that, because that will change the equation. So yes, again, it's over here, and of course your strain energy is equal to your sigma squared divided by 2E times the volume for the first member or the second member. There's nothing really more than this. So like I said, it's a very small chapter. In fact, the next two chapters are small chapters, very small concepts to understand, and then just a matter of applying. Right, so just remember, gradually applied load is a half. For suddenly applied load, it's P times change in length, DL, they're calling it, and then for your impact load, it's that. Sometimes what happens is they give you the energy, and then they ask you, what is the load required? That's basically what you did in the previous, the previous one. We had to find the load to induce a specific one strain energy, right? So they say in both cases, series and parallel, the total strain energy is the algebraic sum of the two. So just basically our typical situation look like. Obviously, this is the, it's probably as hard as it's going to get. I don't see, it's either this or parallel. So we just do this one. I think that other two examples were both self-explanatory. So don't want to spend too much time on this. And maybe we can do one, one worth doing. I'm looking in the textbook itself, which is worth like. Yeah, I'm going to switch now. Don't worry. So why is energy important? That's what I told you. The only reason why it's important is when you're dealing with your failure theories. Now, I can just quickly show you failure von Mises. I can show you why it's important, but like I said, let's just give me a split second. Okay. So, Mr. Kasser just quickly wants to know why it's important, and I do think it's worth showing you this because I mean the section itself, it's really, I don't want to say anything too much about it. But historically, it's been covered. So who am I to just change everything? Okay, so if you actually, I'm gonna open two texts. Sorry guys, I'm just deviating a slight bit, but like I said, it's not difficult. So, but really, and maybe I should include in the slides. Remember, you guys don't cover all the levels of strengths.
So the only reason why I'm asking.
Yes, go for it.
So the only reason why I'm asking is like I understand like the yield stress. Like that will tell us like when materials going out of the elastic stage and going into its plastic stage and is about to fail. I just want to know what does the strain energy of a material tell us? Like why? That's why I'm asking why is it important?
No, that's I'm basically telling you why. So if you look at chapter 19 of the textbook, right? Because I don't think in the new Trotsky, I'm going to share with you now. Trotsky, where's my back here? Sorry. It's this is the reason why it's important. You'll know now. Like I said, I mentioned this in the previous, but we don't have theory failures in this book, man. But if you open your textbook to the last section, failure theories, I've told you something will either fail. We do assume failure, UTS, right? I first brought that concept of failure. Then I talked about yield. But in actual fact, it doesn't work like that. They're actually failure theories, right? And only once you get to applied strength of materials, which is the next level strength, this is where, here they're talking about the sum of the strain energies. I'm assuming everyone can see it in 3 directions. And I'm just going to say a lot of the education you guys have here, it's incomplete. And this is a problem. You guys don't actually see the whole bigger picture. I'm just been fortunate to see the bigger picture, I can tell you in a better perspective. So what it essentially is that you're just summing all the internal energy in different directions. And by the way, we do get to this point in strength. It's when you do it in 3 different dimensions. But like I said, not us. We don't get there. When you quickly go all the way with this, where you really end up is something called the distortion energy theory. It's called the von Mises theorem. The von Mises criteria of failure. And what it basically says is that according to von Mises theory, a ductile solid will yield when the distortion energy density reaches a critical value for that material. And what it talks about, and it says that since this should be true for uniaxial stress also, because you can have materials in triaxial and biaxial conditions, the critical value of the distortion energy can be estimated from uniaxial test. At the instance of yielding in a uniaxial, meaning one axis, the state of stress in terms of principal stress is given by sigma 1 is equal to the yield sigma 2 and sigma 3 0, because in the arguably the y and the z direction no stress. And then basically you have 1 plus your Poisson's ratio. I'm definitely sure that's Poisson divided by 3 over E times the yield squared. So this energy density value, right, will be a specific value. So let's say for steel. You did ask why it's important, so I'm sorry for doing this. But yeah, you did ask. I'm using a typical steel. I'm assuming, what values am I assuming here? 1 plus 0.3, it's your Poisson's ratio for steel, 3 times 200 to the power 10, 9, I'm assuming euro 355. You're going to find out I get a strain energy of 273 kilojoules. Now what it means is that if that value exceeds, if we exceed that amount of kilojoules, that means the thing has failed. I hope that's clear, Alex, because we do get other theories of failure, like the Tresca one, which is the maximum shear stress theory, and there's one more, the Rankine one. These are the ones that I know, by the way. So yeah, I do know some stuff, but it gets frustrating to me also, but yeah. So that's what I'm saying. It's like, I could have mentioned this, but this is the real reason why. There's one text, because by the way, von Mises is, it's the theory which we accept now for failure. Initially, they used to use Tresca and Rankine, but one is good for brittle, and one is good for ductile. Yeah, which is this one, and then the von Mises one is a larger shape. So when you're doing finite element analysis, this is the one we use. Okay, sorry for the overkill. Back to the example. Are you happy? Fantastic. Okay, back to the boarding stuff. Easy stuff. Okay, guys, so what we have here, it's just a series example. I'll probably just do this one, and then you guys can do the parallel one. Hopefully you guys will attempt the exercises, and maybe I'll find some fun ones to do, and I can post it up again. But the relationships are very easy, guys. I don't want to spend a lot of time on something which I deem particularly easy, but I'll just do this one anyway. The concepts are fairly easy to grasp. There's really no other tricks. I'm not gonna be fancy with this chapter. I mean, I could have amalgamated temperature stresses into this thing as well, but I'm not gonna do that. So I'm gonna keep it simple. Okay, so here we just have two rods. They're saying, okay, we have a 200 millimeter rod, 20 in diameter, and has a hole running for. By shots or rod. Let me just sketch this right in. So we've got this. I'm just going for the full rod. So one part is another part. So 80 millimeters is solid, right? So this is the solid part. Then here we have a hole, a 12 mil hole here. So I'm just going to sketch. I'm just going to make the hole something like that. Obviously, your sketch is a better. Maybe I should make it a bit bigger. Yeah. Obviously, you get the idea that is. So that's 120 millimeters, right? Okay. So obviously, it's always fixed here, as I always state, right? No big deal. And you know, Alex, it's strength really comes together nicely in strength of materials 3B or applied strength materials. That's where you really start seeing all the stuff tying in like about. Yeah. Nevertheless, what is this? Where am I now? So yeah, so let's say the rod achieves 12 Newton meter, which is essentially joules of energy, right? So obviously now we have three relationships. One would be force 1 equals force 2. We also know the total change in anything is going to be, see here, like that. We also U1 plus U2. So that's the essential relationships I'll do. You know, if I had time, I would have really made a nice temperature stress problem with this, just to see if you guys can understand. Yeah. So anyway, we're just looking for the stresses. Obviously, the forces are equal. We're always going to end up with these series problems. So we know that the stress in 1. So we can call, I don't know which, we can call this element 1 maybe, and that element 2. And that's just going to be 0.02 squared minus 0.01 squared, and that's the stress 2. That's going to be equal to, I'll tend to that now, 0.02. So I'm just organizing. Yep.
You must swap the 80 and the 120 around on your diagram there. The 80 is on top and the 120 is on the bottom.
Oh, thank you very much. Yeah, if you know, I make such mistakes, but the student makes such mistakes, I kill him. You know, I don't even mark it correct. So yeah, thank you for that. So we just can work at our ratios there from stress 1 to 2. Am I recording? Yeah, good. So yeah, guys, I just recommend just solving all these problems in the back of the textbook. These are the one of the things where you wanna, since you just solve everything. And there's extras I'll let you know. Yeah, and if you get 1.5625, right? Once you have this, obviously, seeing that they give you this total amount of strain energy in this particular rod, you know, I must, Alex, you making me think here what I should do. Okay, so then here we have stress 1 squared over 2 times, they're both the same material. Yeah, so this hardest for these funnels in the gate is going to be 2 different materials here. So let me just quickly see here. Stress 2, well, talking about a volume here. So power 4 times, oh no, we're going to have to now sort this out again, times 0.012 squared. Length in this case is 0.08. Obviously, we have to sort all of this out here on the stress second. And obviously, you can see what's going to happen. We have a 2 by 2 matrix, or just substitute this into that there, then we're done basically. So 2 times 200 to the power of 10⁹. It's a solid portion. Okay. All right, let's just see here. Okay, so can I just get the ratios for each one? So we all have, it's going to be something here, stress 2, something here. And of course, we can just substitute in. It's not a simple 2 by 2 matrix in this case because, yeah, obviously, squared here, so it's not linear. Just want to open my document here quickly. Is it your birds? You can hear them. Isn't it parallel? No, just who's that? Think and Lisa, think of it as two series ball, one hollow ball plus another ball. There's no ball in between. It's just two. It's one ball. We're just considering it as one ball, one element attached to another element, something like that. N series. I don't know if you see that. Yeah, okay. So let's just get those guys. No, it's not. It's no problem, man. Oh, what is my E value? Is it 200 or 100? It's 100. Sorry, guys. It's 100. You see, my elastic molecule is 100. Yeah, but I need a break, man. I'm doing too many things. 100. Yeah, sorry. Yeah, I know. As fun as you can get, you get 2 different materials, that kind of thing. Nothing more, nothing less. Don't see how it can be any more difficult. But I recommend solving all the problems in the textbook. Yeah, that's key. But I'll tell you what is not. I'm not gonna actually concern myself. So, Mr. Takashi, I mean, the only way I would make it interesting, really, is just. But obviously, I have to adjust my values and stuff, and I could have put this formula in here, you know, and then maybe you could have worked out, you know, if something would fail or not, based on the strain energy formula. So, but yeah, nothing more than that. I don't don't think I'll do that. So I guess that's why strain energy is important. And and remember, I did mention to you strain energy has different loads is different. Yeah. Anyway, let's just find those coefficients if I'm saying it correct. I'm just gonna quickly end this off. Times 0.08. And then just divide 2 times 100. I think hopefully this is correct. 80.425 times 10 to the negative 18. Let me just make sure, double check. Yes, for the next guy, plug and play. Plug and play, really. No thinking here. Oh, I even forgot the lengths. I think I forgot the length in the previous one. This is going to be 0.12. I think I forgot the length in the previous one. So I think I made a mistake there. Oh, so that's 0. Yeah, so that's 0.12. And sorry about that. This is 1888.4. I could just call it 5 times 10 to the power negative 18. Let me just make sure that the other one is right again. So pi over 4 times just the area there. Yeah, it's right. They're both to the power 18. Simply now we can just substitute this into here. And I'll just say it's 12 divided by, and this is going to be stress 1. So I'm subbing out stress 2. This is going to be 1.5625 squared times 80.425 times 10 to the negative 18 plus this 1888.5 times 10 to the negative 18 as well. And this, let me just make sure. Yeah, and then we're just going to root it. I think that's correct. I'm hoping I got it right. So we can just get stress 2 and stress 1, obviously. All right. Can we get those stresses quickly?
So stress 2 is 176.61 megapascals.
Okay.
And then stress 1 is 275.87 megapascals.
Okay, sweet. I'm hoping this is all correct. Okay, so that's the first part. Stress is set on each section. Next part is a total change in length. Obviously, because it's a series example, we know what to do here. Stress LE, so member 1. And that was member 1 is 0.120 mole of 100. 176.61. That's 0.08. Also 100, and yeah, obviously if you just sort this out, you should get your total change in length there. Right? So we can find how much this arrangement has extended by. C, they've asked us the load required to induce this energy, and then again, of course, we have to use this model. And they said if it falls from a height of 0.1, so it's 0.1 plus h, and I think we have whoa. Before we get there, it's not that simple. This is h. That's plus your change in length, sorry, which you got there. So let me just work out the change in length quickly. Sorry. And I get 4,723 times 10 to the negative 4 meters. So I can just plug that change in there. So this is the total of 12 joules. You want to see what load induces this. And also, I'm sure this particular chapter, there are ballistics and stuff. People who are into that kind of stuff, they actually use a lot of this kind of stuff. Okay, guys, that's that. Then they basically want the strain energies in each individual member, and the best way to do it is say 12 over here, and then you just take the first one. Remember, your strain energy is equal to this. So we can just find U2. In fact, you can actually just find you can do this for each one, and they should be equal to what is this? To 12 in the end. So I think instead, I'm not sure what the textbook use. So I'll just they use stress 1. So I'll just use stress 2. So I'll just say U1. Stress 2 is going to be 176.61. So guys, I don't think there should be a problem with this chapter, as it's arguably very easy. I think it's very straightforward. And our second section was a 20 mole section with a length of 0.12. Right. And 12, and if you just compute this guy, it's a guaranteed 10 to 15 marks for you. Don't say I never gave you anything. I'll thank the textbook anyway. And if we get that answer, I get 5,87938. And obviously you can just throw around. So is there any questions, students? So I want the question, but I don't want to give ideas for the test. Yeah, then I suggest you just keep it. Okay. So no questions, students? If not, so we can finally adjourn our section. I'll just wait on you guys now. Just go back to the slides. So I just want to say, what I also recommend is don't worry about impact loads and structures like falling loads and weights moving at a constant velocity. I'm not doing that because I'm not doing it. Didn't do last semester and the semester. So section 8.6, you don't have to worry about. Yeah, there's a lot more coming. But hopefully, for the next 4 subjects next semester, I can really make this like fantastic. But yeah, who knows? Yeah, anyway. So no questions, students. Can you get just a few thumbs up, and then you guys can go on I guess a normal 30-minute break, and then we can start in electros. Yeah, thank you, Alex. This DC motor is also right. Thank you, grandson. Someone else, and Elisa maybe. Mr. Manus, Mr. Neto. Thank you guys. Thank you very much. Thank you for that. I have a question here. Hopefully you guys can solve it for me, and maybe we can discuss it maybe next time. And thank you. So yeah, so let's meet at 12:30. Go outside, get some fresh air. We're starting with DC motors. Nothing too heavy. I think. For electrodes, it's going to be just essential continuation. Not a continuation, but yeah, you'll see it's not that difficult as well. But I'm really looking forward to mom because that's going to be very, very interesting. Oh yeah, let me just quickly check something before we end. I just want to share a program quickly called SolidWorks. Oh, what's going on here? This is my installation corrupted. It's impossible. Just give me a small second. And I'll just start with for electrodes. Whoa, that's a problem actually. It's going to be a massive problem. Let me just open it again. I just want to see if I can share it. Okay, it's working. No, what's going on? Okay, it's open. Oh, okay, cool. It's fine. Fine, it works. So let me just share. Stop. So let me know if you guys can see it. So, you know, I've asked you guys once about drafting and who draws things and you know, the program I was taught on to draw, and it's probably one of my. I'm not an expert. I haven't practiced in a while, but yeah, you can literally draw anything on these things. You can model anything 3D. But the reason why I showed you this was this program, because I will be using it. We learned this. We know we have drawings 1 and we use AutoCAD, and in the next level drawings we use SolidWorks. It's also a program called Inventor, which is similar to this. What I want to show you is, yeah. So this chair I didn't sketch myself. It's part of SolidWorks' tutorial packs here. And what's cool about it, what actually happens is this tutorial which I'm looking at here is you basically, they show you how to run this simulation study on this thing, man. So in a nutshell, we basically we have the chair. It uses finite element analysis, and then we basically load the chair up on the center here, and then basically we load it on certain parts, and then I can tell you basically how much the chair is displaced. And these colors here tells you just the amounts in terms of magnitudes. This can also be done for stress as well. So you can actually change the results and see stresses in different directions. Obviously, normally it'll tell you once you've exceeded the yield of the thing. So yeah, so I just thought I'll show you this. I want to actually conduct a small thermal expansion study because you can actually, they've exaggerated, you know, like you can show how it expands and stuff. Here's another static analysis you can do. So basically they're loading that on that boss, if what you call it on that opening section, you can say what material it is, and you load it up there. In the end, you're going to always end up with your mesh, and then you end up with something like this. And I can see that von Mises thing, that's the criteria we use, and it's basically telling you where your yield strength is. And it tells you where this 8.9 and 8 is, that's your yield. And obviously we reach it. So basically what it means that over there on those round circles, probably the lift tests and the corners, obviously some stress concentration, that's where it's going to rupture, most likely to rupture there or there. So anyway, oh, you guys can't even see that. Yeah, you guys can't even see that part. I thought that I just realized now, but anyway, yeah, I'll maybe just quickly see. Oh, it's on a separate document, that's why. Yeah, so quickly, I'll just quickly share it with you. This is the component I was talking to myself with. Thank you guys for saying nothing. Yeah, it's gonna come up now. That's the component. Yeah, so yeah, so that's what that's the kind of von Mises stress this thing, just in relation to, just to make you guys aware. Yeah. Okay. So and those green areas are the parts I was talking about. It's telling you exactly when it's past the yield. Yeah. And this uses the distortion theory. Anyway, guys, I'll see you later on. Enjoy the small break, and get ready for. Yes, on moms, you need a bigger set squares, and this is yeah, and a protractor. I did mention that. So please make sure you get that tools for what is this